Okay, so we're rolling a dice, and unlike the binomial, where we said we're going to do something 10 times, or we pre-specified a number, we're going to roll until we get a 5 or a 6. And the question is, what's the chance that happens in exactly 3 tosses? Let's see, what did people say? All right. Ooh, okay, this is wonderful. We have a lot of people who said 1, 1, 1, which means we're going to learn something. Seems the most common answer other than that was, what, 4? Ooh, we got some dividing by 2/16s, okay, because you roll 3 dice. Very nice. Most common answer other than that was 4 over 27, and that is correct. Gary, would you like to explain how to get 4 over 27?
We will, but we'll run through a couple things. So basically, so let's write it in terms of the geometric distribution. And define things. Oh, we have a weird thing going on here. Just a second. I'll tell you what the weird thing is in a second. So the clip has been broken for our microphone, and so I've tied it around my tie. So we'll see if this actually works decently. It doesn't sound so bad. Okay. Okay, we're going to toss a fair die until the first 5 or 6 is obtained. Let x equal the number of tosses required to get that first success. Okay, so I'll leave that kind of unsaid. So we've defined our random variable, and then the distribution of x. Is geometric with parameter p equals 1/3. Okay? So the probability x is equal to 3 that we have to go 3 tosses, or you could call that p of little 3. In order to go 3 tosses, first of all, we have to fail twice. So we're going to take q squared. In other words, we didn't succeed on our first toss. We didn't succeed on our second toss, but we do succeed on our third toss. Okay, and again, the probability mass function for the geometric distribution is simply q to the x minus 1, or 1 minus p to the x minus 1, because those are all failures, and then we get our success p. Okay, and so we've got 2/3 squared, didn't succeed for the first 2, and then we succeeded with probability 1/3, and that's where we got our 4 out of 27. Okay. So I'm going to mention a couple other questions here. We're going to look at the questions, and then we're going to come back to a slide of last day and just kind of go through something that seems a little tricky when you first see it. Let's see, I have to go to my HDMI laptop, and I don't want that yet. I want this. So we just did the first question, assuming independence between tosses, which was pretty safe there. So we solved that question, but now let's consider this question. What's the probability it will take no more than 3 tosses to get the first 5 or 6? Okay, so one way you might say to yourself is, okay, that's going to be the probability that x equals 1 plus the probability x equals 2 plus the probability x equals 3. Does everybody agree with that? Anybody disagree with that? That the probability that x is less than or equal to 3 is the probability x equals 1 plus the probability x equals 2 plus the probability x equals 3. Well, I can't disagree with that. And how about this question? What is the probability it will take at least 8 tosses to get the first 5 or 6? Okay, well, at least 8 tosses means 8 tosses, 9 tosses, 10 tosses, 11 tosses, 12 tosses, 13 tosses, 14 tosses, 15 tosses, and heading off to positive infinity. That's a lot to add, right? That's definitely a lot to add. So you may say, well, you might say, well, Humphrey, why would you be so foolish to try to add everything from p of 8 up to p of positive infinity? Well, there might be an easier way. What would be an easier way? Give me an easier way. What would you say?
Find the probability it happens in the first 7 and then subtract that off of 1.
Okay, so you say to get the probability of the first 7, how about we do p of 1 plus p of 2 plus p of 3 and so on up to p of 7, subtract that from 1? Who would like to do that? Like to do that? Good. Lots of people would like to do that. But there's an easier way. There's an easier way. And what we want to do is look at the easier way to get this. So we go back to a slide of last day. And this is this one right here. And focus on this one here. The probability x is greater than a equals q to the a. So the probability x is less than or equal to a equals 1 minus q to the a. So that seems like, you know, it might seem like a little bit of gibberish. And what did I write on? That wasn't my, excuse me, I grabbed my wrong paper. It's okay. Okay, nicer paper. Okay, this business about in order for the first success to occur after the 8th trial. Okay, so a is just a placeholder for the value of x. What must happen for the first 8 trials? Give yourself a number. In fact, let's go back. Let's go back to that question there. The number 3, what's the probability it will take at least 8 tosses to get the first 5 or 6? If it takes at least 8 tosses to get the first 5 or 6, what must have happened for the first 7 trials? We failed every time.
Yeah.
We failed every time, right? So, the probability x is greater than or equal to a simply means that for the first 8 trials, we must fail for the first 8 trials. I'll mark it that way just so we can don't read it as a word. First 8 trials. And this probability is q to the a. So, the probability that x is greater than a equals q to the a. If we were to ask what's the probability that x is greater than or equal to a, what would be our answer on that one? Yes?
Q to the a minus 1.
Q to the a minus 1. In other words, we simply failed for the first a minus 1 trials. Now, we can use this to work out sort of cool complements. If I want the probability that x is greater than or equal to a, that's just going to be 1 minus, that wasn't a greater than or equal to a, we just did that one. I want less than or equal to a. Probability x is less than or equal to a, well, that's just the complement of the x is greater than a. So I do 1 minus the probability x is greater than a, and so that's just going to be 1 minus q to the a. Or if I wanted the probability that x is less than a, I'm going to do 1 minus the probability that x is greater than or equal to a, and that's going to be 1 minus q to the a minus 1. So you've got everything you need there to solve our next mathematized question. Our next mathematized question. And let's give them a short period of time on this one.
Yes.
Short,
Okay, well,
we don't want it to do the long way.
Right. Okay, we're going to give you enough time to do this the short way, but not enough time to do it the long way. I guess we got to put up the question, or else you're really screwed. Okay. So it is the second of those questions, and the numbers are small enough that you can type them into the computer. And if you've been paying attention, it should be a snap. Okay. No more than 3 tosses. No more than 3. All right. 30 seconds left, 20 seconds left. Put in your answers. Hopefully you did it the short way. If you do it the long way, you will run out of time.
It depends.
It depends, yeah.
Should have gone 5 tosses.
Okay. Okay, put in your final guesses here. So, at least for me, half the battle is figuring out what no more than 3 means. Right? Does that include 3 or not? No more than 3. Okay, if you figured it out and you used the right formula, it's quick. Okay, I'm pressing the button.
So Alexa's still coming in.
Hurry up, people. Okay, I'm doing it. Let's see. People said, all right. Out of 59 people, 19 people said 19 over 27. Some people said 8 over 27. We got all sorts of answers. The most common answer was less than half the people. So 59 people, 19. 9 people said 111. That's a good one. Maybe we should write this one down in terms of the kind of thing Gary's been talking about with X and A, and then we'll give you a chance to revote. Let's go to the doc cam here. And the HDMI. So this question is one of these formulas. What is it? The thing you got to do is you got to convert no more than 3. Which one is it? No more than 3. Is it greater than something, greater than or equal to something, less than or equal to something, or less than something? And if you know the right one, you'll figure it out. So let's see. There's no more than 3. Does that include 3? It's not more than 3. So is 3 included? I think it might be. I think it might be. Okay.
If you're saying there's no more than 3 children in a family,
Yeah. This is what
if there were 3 children in
this
a family, that's no more than 3.
Yeah, that's what I tell my wife every day. How many burgers did you eat? I ate no more than 2 burgers.
Okay.
I stopped at 2. Okay, let's reopen it, and you guys can have a chance to vote again. Let's see if you can do it a second time. Let me try to get this working. I gotta. Repeat the exercise, and then I go into the revote. So not a big majority. I think you guys were mixed up onto which one it is. Maybe we'll give a hint. We'll put the formulas back for a second. And you got to figure out what the Q is and all these things. Which formula are you going to use? Okay. Okay, one more minute. Let's do 1 minute, and then we'll take it up. So again. Okay, we're up to 50 people. There's 9 people left, I guess, that need to put in their answers in the last 10 seconds here. So put in your guesses. I guess 111 is still a good answer. If you really don't know, put in 111. That helps us figure out how slow or fast to go, how quickly to move on to the next thing. Okay, time is up. Let's stop the thing, and let's see what you guys said. I want to flip these around. Let's make this one the dock cam. Make this one the laptop. Okay. Doing the old switcheroo. Okay. Let's see. What did people say this time? All right. Now almost everybody is in 19 over 27, and that is the right answer. Very good. So 19 over 27, and the smart way, again, is to figure it out, is if it takes no more than 3, then the only way this can go wrong is if you went fail, 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 and the first 3 failed, right? So if you typed in 8 over 27, you answered the opposite, right? 19 over 27 and 8 over 27 are complements. And 8 over 27 is 2 cubed divided by 3 cubed is the chance of going missing the first 3. So it takes no more than 3 as long as you don't miss the first 3. So the right answer is sort of 1 minus 8 over 27 is 19 over 27. You all got that right with the help of the formula. So very good. All right, do we have anything else to say about geometric variables? Let's put these back on.
A bit.
A bit. Okay.
A bit. Where are we back on there? Okay, so we're going to put this one up as a mathematized question. What is the probability we'll take at least 8 tosses to get the first 5 or 6? Just answer that within, I'd say 3.2 seconds. And we'll take 3.4 if you wish. Just write it down yourself what you think that would be. Kind of the point here is it's really not about trying to figure out which equation works. It's just kind of like thinking of the logic of what is going on. If you toss it at least 8 times, you are going to get, it's going to take at least 8 tosses to get your first success. As long as what? As long as you failed for your first 7 tosses. And failing for your first 7 tosses is just going to be 2/3 to the 7th power. And then you have answered your question. So that's just 2/3 to the 7th power. I'm not going to write it down. Okay. Just a couple graphs. I'm going to post these. No big deal. First of all, this is not a graph for the entire probability distribution for a geometric random variable. Why is it not the graph of the probability distribution of a geometric random variable? Well, it's part of the graph. But remember, x takes on values everywhere up to positive infinity. And if I try to keep going with the graph, it'd keep on going and then it'd bust right through this wall, which would damage the wall and go out through the building, and who knows who it might injure out there. So it's been truncated at x equals 20. But there's an important thing to see here with the geometric distribution. The probability, so this has got a p of 0.5, but one of the things that happens for each value of x is the probability for any particular value of x continually goes down. It has to go down because to get to any higher value of x, you've got to get some failures first. And those failures each occur with probability of q. When q is less than 1, you're always going to be multiplying by something that's going to keep reducing that probability as x increases. And just a comparison of a couple of different geometric probabilities. There's p equals 0.5 versus p equals 0.2. Something that the probability of success is lower. But the thing here, again, is part of the cumulative distributions, is that the cumulative probabilities naturally do start keep going up. Cumulative probabilities will generally always increase. They can't go lower anyhow, but they'll typically continue to increase as x increases. And so, for example, the cumulative probability for x equals 1 there is 0.5, because that's the probability x equals 1. But the probability that x is less than or equal to 2 is going to be the probability x equals 1 plus the probability x equals 2. So you get 1/2, 3/4, 3/4, 7/8, 0.875, and so on, 15/16, and so on for the cumulative probabilities. And so when p is, just a sec, I think I'm walking on my microphone. My tying technique did not work all that well. Wonder what I could do about that. Nothing. Try this again. Yeah, so the cumulative probabilities do increase at a slower rate for a smaller value of p. Okay, enough of the geometric for now. Okay, so now we're going to go into another big topic, and this one kind of takes a while. Again, a little bit of time getting our head wrapped around, because parts of it are, well, confusing. But a sec. We look at it, our job to get you a little bit confused here, so that when you hit your higher level courses, when you go into your next courses, your second year, third year courses, you'll say, oh goodness, I've already gone through the confused stage. I've got this totally under control. Okay, let's see. Oh, we still got, what have I got? I got HDMI laptop, USB laptop. I don't want that, right? I want HDMI laptop. There I am. Okay. I think. Okay. Back we go on that. Okay, so we have been discussing discrete random variables, and discrete random variables, we've done some generic ones. We've also done special ones. Binomial random variable and geometric random variables are two examples of what we call special probability distributions, which have discrete random variables associated. So now we're bringing this topic of continuous random variables. So we got to kind of like get our heads wrapped around what do we mean by a continuous random variable. So first of all, we have seen that discrete random variables take on either a finite number of values or a countably infinite number of values. The binomial distribution was an example of a distribution where there were a finite number of values. You know, x could take on values, integer values of 0, 1, 2, and so on up to n the number of trials. Whereas the geometric distribution, the random variable there, which is the trial on which you get your first success, if we define that as our random variable x, we said, okay, it could happen on the first trial, the second trial, but we could go off to positive infinity. So that's what we call a countably infinite number of values. Okay. Now, continuous variables can at least theoretically take on any value on the real line over some interval. Okay? And once we get our heads wrapped around this, there's kind of, it's kind of cool. It's kind of cool. And let's think about, we're going to look at some examples in a moment. So even though we say that at least theoretically take on any value of the real line over some interval, in practice we will only measure to a certain number of decimal places, okay, to a certain level of precision. And there's a couple reasons for that. One can be the measuring equipment. The other can be simply how many decimal places are actually useful to us. So here's some examples of continuous random variables, things that we measure on time, length, area, volume, weight, temperature. These are simply some examples, are a few simple ones. So consider measuring the weight of something. It doesn't matter. It could be a person, could be an apple, anything like that. You're going to measure it to a certain number of decimal places, but nothing says that you couldn't go to an extra decimal place. Would you agree? And if you had the equipment, you could go to another decimal place and another decimal place. And you could just keep getting down to more and more and more decimals. And there's really no limit to how many decimal places you might be able to measure if you had the equipment to do it. So we have previously defined the probability mass function for a discrete random variable, and this is just a recall that what that does is it assigns probabilities to each possible value of the random variable. Okay, again, we had probability mass functions for the binomial, the geometric, and in fact it could be any discrete random variable. We could put probabilities on each value of that random variable. Now, and I will be posting these slides if you find there's too much writing to do right now. So we bring up this idea now of something called the probability density function, not a probability mass function, but a probability density function for a continuous random variable. And here's the key thing, is this function will not assign probabilities to each possible value of the random variable. Instead, it's used to assign a probability that the random variable will fall within an interval of possible values. So, again, we're going to try to bring this in a intuitive way. Let's leave that for a second. So this is really a key thing to get down, and at this point, you're kind of like memorizing it, but later on, it should get to the point where it feels intuitively right that the probability density function, it's called a probability density function, but it is not calculating probabilities directly. We will see what it does for us. So I'm going to move on. I'm going to leave one of these up for the moment. I'll freeze one. I'll freeze this side. Freeze. Hey, doesn't want to freeze. Okay. 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 We're going to consider some event that will occur with certainty in a specific time interval. Okay? And it might be, in physics, it might be the emission of a rare particle that we can be certain it's going to occur at a certain time. But I think kind of a better one is to think of something so simple as you're expecting a delivery. And your guaranteed delivery is going to occur between 5 p.m. and 6 p.m. with certainty. Okay? But you don't know when that delivery is going to be made. But when they make that delivery, they're going to ring the doorbell. Okay. And what we want to do is think of the very first dingle, the very first time that doorbell goes. I don't want to think that, well, that doorbell rings for this many seconds or anything, but I'm trying to think that particular point in time where the very first ding happens. Okay? So we said that this is going to happen between, what did I say, 4 p.m. and 5 p.m.? I can't remember when I had it delivered. Pardon?
You said 5 and 6. I think.
Between 5 and 6. Oh, that's because I got a delivery from IKEA yesterday. But now, I'll tell you why I'm confused. They said it was going to be between 5 p.m. and 9 p.m. and they delivered it at 4:30 p.m.
Which time zone were they?
Pardon?
Which time zone were they in?
Well, it was supposed to be my time. But no, it was okay. They notified me that they might be able to get it there early, which was fine with me. Okay. So, anyhow, it's going to occur between 5 p.m. and 6 p.m. Okay. Now, what we're saying is you have no reason to think that any particular interval of time is more likely than the same interval of time to have the doorbell ring. And so, for example, if I was to consider 15-minute intervals in that hour, okay, let's just kind of think this out. I'm kind of a simple man here. I got to think of this. It's going to occur somewhere between 5 o'clock p.m. and 6 o'clock p.m.
Gary, do you want to turn the doc cam on?
That would make it easier to read, wouldn't it? Okay, we can do that. We can do that. I'm just going to put that. I'm going to go up here, the doc cam. We've got that showing up this. And so what I'm saying is going to be equally likely to show up between 5 o'clock and 5:15, that first dingle, as it is between 5:15 and 5:30, or 5:30 to 5:45, or 5:45 to 6 o'clock, or in fact any other 15-minute interval in there. And in fact, I don't even have to have the interval being continuous. And if I went to 5-minute intervals, again, every 5-minute interval is equal. And so if we were looking at when that thing might ring between 5 o'clock p.m. and 6 p.m., what we're thinking of is that probability is uniformly distributed over that time. Now, what I can consider is that I've got this time, and it's gonna ring somewhere in there. It's gonna ring somewhere in that time period, and the probability is gonna be evenly distributed. So what would that mean? That would mean something like probability is going to be somewhere over that interval, but it's uniformly distributed. And, okay. So if I was to say, what's the probability that the doorbell is going to ring between 5 o'clock and 5:15, what would you tell me? You want to tell me something. What would you tell me? Between 5 o'clock and 5:15, uniformly distributed over this hour. So if we say the doorbell must ring in that period of time, and it's got an equal chance of any interval, what would you say? 25%? How did you get that?
Just took the 100% intervals.
Yeah, you said for any 15-minute interval, you said this is this 15-minute interval. You took 15 over 60. There's 60 minutes in there. 15 over 6 is 0.25. Okay. How about for any 1-minute interval? What would you do for any 1-minute interval? You want to give me an answer on that one, right? 1 over 60. 1 over 60. I don't know what 1 over 60 is. It's 1 out of 60. It's 1 out of 60. Okay, 1 out of 60. How about in any 1 second interval? Okay, so I'm gonna like time it right to the very start of when that thing starts. Any 1 second interval. What would you go with? We have to do our mathematics of that one. We have to figure out how many seconds there are in a minute and that kind of thing and so on, but I bet you got an answer. You got an answer for me, right?
Yeah, 1 in 3600.
1 in 3600. Ooh. Could I break the second up even smaller? Yes, I could do. I could go into tenths of a second, hundredths of a second, thousandths of a second, billions of a second, trillionths of a second, finer and finer and finer. What's going to happen to that probability? It's going to get smaller and smaller and smaller. Okay? Kind of interesting. Okay. Yeah. And I'm just going to write smaller and smaller intervals. Interesting. Smaller and smaller intervals. Okay. Let's think about this assigning us probabilities now. 0 to 60. I'm going to make this the 0 point, and I'm going to do it in minutes. And I'm going to call this x equals time in minutes. from time 0. In other words, from the start. Okay? And this length here is 60, 0 to 60. And so what do I need to do to make this total area equal to 1? Okay, this is a probability here. Total area is equal to 1. And so this thing here, which I'm going to call little f of x, is going to be, well, if this is 60 long, and I got to make this total area 1, this value here has to be 1 over 60. Do you agree? Okay. So if I say in the first, in a 1 minute interval, 0 to 1, that's got length 1 times 1 out of 60. That gives me the 1 minute interval. And it doesn't matter where I go in that interval. If I take any interval of length 1, the height of that little rectangle is going to be 1 out of 60. But I can make that narrower and narrower and narrower there and get it all very fractional. And the idea is total area under the curve, which is in this case a rectangle. A straight line, technically under a straight line, is 1. Probability that x falls in any time interval let's call that time interval AB equals the probability that A is less than X is less than B is going to be the length of the interval.
Here, you're just off the bottom there.
I'm off the bottom. Oh, that's going to be B minus A divided by 60. I should specify that A and B have to be within these bounds here, not outside of the bounds, but I'm going to leave kind of some of the niceties for as we kind of define this a little clearer mathematically. But the point is we're going to just take that distance and we're going to divide it by 60. So that interval can be, and where's this thing going again? Here I am dragging my thing around. It's kind of irritating. Okay. How small can the distance between B and A get? Well, there's no theoretical minimum distance. It can collapse down to 0. Now, how many of you done integration? How many have done integration in a... Not very many of you, okay? So not many of you have done integration yet. You're going to find when you do integration and you come back to statistics, you're going to use it extensively, okay? You're going to use integration to find areas under a curve. One of the things you are going to come up with is the argument that the area under a single point on the curve, the area is 0 but we will use integration to find the area between 2 points A and B. When we have more complicated non-geometric curves like this. This one we can work everything out very easily. Okay, so we can define various types of distributions with these, not just nice rectangular ones. These are the continuous uniform distributions. We'll show you a couple others that are just a little bit more complicated, but again, the key thing is to think of areas under the curve, and that's what we've done today, and that's all we will do today. And on Wednesday, we continue. Now, does that give you a good starting on Wednesday? Because then you can.
Yeah, I'll take it.